So firstly, yeah, I've been using KDB for almost like 20 some years now. Was at UBS EFX. And those of us who have been doing KDB for a long time, we know how difficult it is to keep trying to optimize Q code. Like you keep staring at your code for the longest time, thinking, how do I fix this? How do I fix this? And it's tough, And even if I can get it run twice, 2 times faster, 3 times faster, that's something to talk about. So 30 years of innovation, best-in-class DB in the industry, high-performance interfaces, 100% CPU, you can maximize all the memory utilization, maximize infrastructure TCO, and so on. So we've kind of come to a point where, we have done everything possible to get the best out of KDB. And so the question was, what can we do to take this to the next level while keeping, the reliability, the integrity, the performance, and other factors? So the answer to that, turns out, has been this thing called the KDB Plus GPU library, which is still in development, but it has some really interesting aspects. The idea is that it's going to be it's a Q-native library that offloads KDB Plus operators to the NVIDIA GPUs. We are observing close to 5 to 100x speedups on matrix operations, as of joins, vectorized transformations. And the core idea is keep tables, tensors resident on device, move the compute to the data. But more importantly, perhaps, can we make it easy? It's really tough to get GPUs to work, just to configure them, set it up, and things go wrong. So the GPU library, good, that executed. Okay, that stopped working literally. Okay, and I've been you see the number of times I clicked on the thing, 48 times now. So import OS works fine. So what we have here is libgpu.so. And it loads the gpu.q file. And what I want to show you are a few examples, stuff that has some primitives that have been written in the GPU library that speeds up basic primitive operations, whether it's VWAP or, just some median deviation, etc. So I have loaded the data set. It's NASDAQ 100 cleaned up data, timestamp, OHLC, adjusted flows, and so on. Just to give you confidence that I'm actually really running this live. Yeah, it's an A100 SXM4, 80 gigs of memory. So I'm going to load the data in and just simulate some data so that I have like 10 million records. So I have timestamp, close, same time, price, size. So there's 6 different use cases here. First is the end-of-day sorting. Sort large end-of-day tables on GPU. Second, GPU select with .gpu.select. And this is one of the most interesting things, right? So it's like a drop-in replacement. So you do .gpu.select and you wrap the functional form of select and it runs it on the GPU. VWAP on GPU, compute VWAP per symbol. As of joins for GPUs, custom kernels, matrix multiplication. So for the first use case is end-of-day sorting. So the idea here is that can I sort 10 million records on disk, in memory, in GPU, sort EOD records by same time on the GPU to shorten the batch windows and enable more intraday reruns. Okay, so I'm going to have 3 different numbers here. One is sorting on disk, sorting in memory, and then finally sorting in GPU. So sorting that table on disk, 2 seconds, 39 milliseconds, 1.366 in memory. The same data is also in the GPU at 62 milliseconds. If you do the comparison, these are not toy examples. I'm using large data sets to, I'm not doing full bar, mouse, and all that stuff. This is real data and it's sorting it. And 62 milliseconds. So if you compare the time difference, in-memory sort, that's the best we can get, XASC in KDB. And the same thing in the GPU, .gpu.xasc, 62 milliseconds. So we have a 32x speed up. So the observed speed up 12 to 15x, in this case 32, shrinks the EOD window, reduces overnight run risk, allows more frequent reconciliation, capacity supports larger universes, histories, and so on, right? So you suddenly have this 10x, 20x speed up just by switching from XASC to to .gpu.xsc. The next thing is GPU select. So you have all these select statements, and can we make it so simple so that we can just take the functional form of the select statement. You can just do like a parse, right? And then wrap that in .gpu.select and see how that works. So the query here is select some size by sim algo from the same table. The CPU time to calculate it is 1.232 seconds. It's 10 million records. Same thing in the GPU is 137 milliseconds. And as I said, functional form, and those who are familiar, right? TCBA table, no group bys, no constraints, group bys, and aggregations. And the observed difference is 9x speed up on just a plain select statement, right? I didn't have to do anything fancy, no spending hours going through the code. Business implications of the observed speed up is 10 to 14x. You can just do so much more. Suddenly all your code is automatically running 10x, 20x faster. The third example is GPU VWAP. The idea here is, can I compute VWAP per symbol on the GPU using the VWAP expression? And I'd be using .gpu.select. They made it really easy to move the data back and forth between GPU and CPU. We just do a .gpu.table to GPU and .gpu.table from GPU, and it moves it back and forth. So on the CPU, it was 107. So we're going to run the same thing on the GPU. So we move the same thing on the GPU over there. It's a 5x speed up on the VWAP. It can be a lot faster. I mean, there's a lot going on this machine right now, but you see all the steps that I had to do over here, but .gpu.select, the same query, the same VWAP query, wrapped into .gpu.select, and I pull the data back into memory using .gpu.table from GPU. Next, transaction cost analysis. This one is a bit more intense. We have 20 million records in the trade table, 200 million codes, and it's .gpu.ha that every one of us use, right? And age is already fast. Like, somebody said, you're already the fastest on the AHA. Like, what else are you going to do? So 20 million trade records, 200 million codes. So I ran the stuff on the CPU. Let's just give a quick comparison of what it was. 3.63x speed up on AHAs. What it means is now you can run 4 times more AHAs. And it's just, I'll get to something else towards the end, which will tell you that you can just do so much more. 3.6 might not seem like a big deal, but all I'm telling you is just get one GPU card and you run these operations, and your code's going to run like 5x faster. One of the other interesting features is custom kernels. So here, if you have some very specific operations, TCA analytics, you could use .gpu.jit to register them. There's a lot of reading material behind this, but one of the good examples that we have here is doing time lags, multiple as-of joins, right? So the idea here is that can we do 50 AJs across 10 millisecond time lags, and so we want to create 50 columns, get the mid prices and the GPU version that run the same GPU 50 as-of joins using GPU acceleration. So today, to run those 50 AJs, 16 seconds, on the GPU, 7 seconds. This is a very common operation. Again, we see a pretty significant speed up. The final example is with matrix multiplication. Just for the heck of it, I said, why don't we take a 1 million, just create 1 million vectors of length 1536 to simulate OpenAI embedding vectors. What we want to do is to compare MMU with the GPU version of the MMU. So you want to find the shortest distance, right? So it's you have 1 million embedding vectors, you have your query, and you're doing a RAG operation as you do in a vector database. It's L2 norm. It's 400x speed up on the MMU. And this is live. Sometimes I would have loved to just show this on the video. I was almost going to do that today, but it still worked, and this is real. And again, just to get, and I guess one of the most interesting things with this is this: it just costs $1 an hour on this GPU card. It's A100 for $1, $1 an hour. I just have everything running 10 to 500x faster. Again, just to tell you that this was real, yes, NVIDIA SMI is going to show me that it's an A100. So, but what does this mean, right? So what is the implication? I mean, it's all good. The technology part is great. All of that is fine. Firstly, I think the features are very interesting. It's like a seamless drop-in replacement, right? And simple migration, .gpu.to device, .gpu from device. Multi-GPU scaling, that's very interesting. This is an 80 gig card, so there could be questions like, okay, I have a petabyte or something, right? So if you have 10 cards, you can pitch across the GPUs. So instead of pitch applying going across CPUs and cores, it can pitch across the GPUs. GPU power table operations, so the familiar operations being run with a GPU DSL, and GPU direct for direct, disk to GPU transfers. So finally, to wrap it up, in terms of what this means, speed is great, it's ultra low latency, high performance. We're trying to take it to the next level, and so on. So in terms of algo backtesting, getting sample subsets, so intraday strategy reoptimization, if we're doing like nightly offline updates or signal to order latency. Before is that, but today with post GPUs, we could potentially be doing backtesting on the entire tick level data, intraday real-time on-demand reoptimization, sub-second feature calculation, scoring, and so on. And what all those really comes down to is the ROI. What does this mean in terms of the returns that you're going to get? 4 to 5x more strategies in the same window, capture short-lived alpha, and so on. Same thing with TCA. Instead of doing market impact, recalibration can take hours, but do market impact for hundreds of lags, full sweep in seconds, better vendor selection, slippage reduction, same-day TCA reporting, and so on. So there's a whole set of new types of use cases that this thing actually opens up. And, like I said, we've all been using KDB for a long time. We know how tough it is. But to see that there is actually something that is real, that actually works, and it makes things run so much faster. Like I have personally never seen in the last 20 years, right? That's really amazing. And we believe this could be a step change in the tick database paradigm, right? You have breakthrough time series performance, KQ flexibility at GPU speed, multi-GPU parallelism, and maybe it also opens up opportunities at the at-trade level, right? Not just pre-trade, post-trade. Yeah, at-trade, you could say FPGAs and so on. But are there ways where we can run KDB if it's running at GPU speed? Does that open up some new ideas? And then you have compounding advantage. And finally, the quantifiable business returns to reduce time to market, execution quality, quant productivity, higher efficiency at lower TCO. And I guess, there are lots of other products in the market too. I was speaking with someone earlier today, and just like I was in the tube, there are these ads about some database or something. We already know KDB is fast, and I'm like, if I can now do this like 10x faster, like just bring it on. This thing works and it's real. So thank you. I'm happy I was able to share this with you.